Okay, so now we're going to go over three theorems. Fermat's little theorem. So you guys may have heard of Fermat's last theorem. It's the same Fermat, same guy. Euler's theorem, which is a generalization of Fermat's little theorem, or builds off of Fermat's little theorem, and then the Chinese remainder theorem. So Fermat's little theorem says that a to the p is equal to a mod p prime for p prime, or for prime p. So if we have a prime p and we have a so we'll just go with a standard notation of a is between 0 and p. I guess it can be equal to 0. Then we have this. And if it's equal to 0, then we have this as like super clear, right? Because this is 0 to the p is equal to 0. But so let's go about proving this guy. So start by proving our base case. So it checks out for 0. 0 clearly works for both 0 and 1, and for 1. So we'll use 1 as our base case for the sake of simplicity. So now we will assume it works for a minus 1 and try to show it works for a. So this is slightly different from our normal system. We usually do assume it works for n and then show that it works for n plus 1, but this is entirely equivalent. We're dumping from a minus 1 to a, so we're just doing a single jump. That's fine. So a to the p is equal to a mod p is equivalent to saying that a to the p minus a is congruent to 0 mod p. So we can just rewrite it like this, and then we can factor this guy out as a to the p minus 1 sorry, not like this. We were going to write this as a to the p minus 1 plus 1 minus a. So this is this guy. We can do our binomial expansion to turn him into third time's the charm. My notes are a bit messy here. The p should be out here. So then I can expand that out just using binomial theorem into this guy. But so for p choose k, for k not equal to 0 or p, so this is going from k equals 0 to p, 1 to p, then it's going to be, 0. It's going to be not co-prime with p. So each of these guys, except for these two cases, is going to involve a k. It's going to involve a p. It's going to be a multiple of p. So that is going to be congruent to just the highest and the lowest surviving when I do mod p. So that's going to be equal or congruent to p choose 0, and that'll be a to the 0, or sorry, a minus 1 to the 0. It's the same thing, but plus P choose P times A minus A. And this is all mod P. So now I can rearrange this to say this is going to now be equal to, so this right here is just 1. This is 1. So this is A minus 1 to the P minus A minus 1. When I move this inside, it becomes a double negative now, and that's all mod P. But guess what? We assumed that we assumed for the case A minus 1, we have A minus 1 to the P is equal to A mod P, which is still, again, equivalent to A minus 1 to the P minus A minus 1 is equal to 0 mod P. So then this guy has to be congruent to 0 mod P, because I'm just I now have 0 minus 0 mod P by just basic addition of modular arithmetic. So I'm not going to go through and prove Euler's theorem, but Euler's theorem says that if A and N are coprime, or relatively prime, these things mean the same thing, they just share no factors, then it is A to the congruent to 1 mod N. So this can be pretty easily adapted from an alternative proof, from the one that we did of Fermat's little theorem, but it's slightly more complicated, not that bad. But this is Euler's theorem right here. Okay, so the last one that we want to talk about is the Chinese remainder theorem. It's also sometimes called Sun Tzu's remainder theorem. The story has to do with an ancient Chinese general reorganizing troops into different size units and seeing how many are left over to calculate the exact number of troops that he has. So if we have A, B, N, and M, and the GCD of M and N is equal to 1, then we have, and Z is equal to A mod, congruent to A mod N, M, and Z is congruent to B mod N, then there exists a unique Z that solves this. The above equation. Such that Z is less than M times N. Because this last requirement is necessary, because otherwise I could just add Mn to my solution, and it'll be pretty clear to see that that would still be equal to both A and B mod M and N respectively, congruent to. So we know that Z is equal to A plus mx, and that is equal to B plus ny. Just because this is the definition of it being congruent to A and B mod N and N respectively. So then we can rearrange this to say that B minus A is going to be congruent, is going to be equal to mx minus ny. So I just rearranged this line right here. And right now, I know that this guy right here is equal to k times the GCD of A and B, right? Times the GCD of M and N. Just by the fact that this is a linear Diophantine equation with a solution. And now you can just apply the extended Euclidean algorithm. I showed you guys the abbreviated Euclidean algorithm where you don't keep all of your track of all of your notes as you go along. You don't keep track of how everything, you don't keep track of what the actual solutions to X and Y are. Here we want to know what the actual solutions to X and Y are. I attached a video in this series covering the extended Euclidean algorithm, just giving you guys a few examples. It's not really conceptually different. It's just to keep track of everything. So I strongly suggest you look that up, and that will show you that we will be able to find a unique X and Y, or we will be able to find a first X and Y such that this will work. So that's going to be enough to show that there exists a solution, but we also want to show that there exists a unique solution such that it's less than Mn. This is also, you can think of it as there exists a unique solution mod Mn. So to show uniqueness, what we generally do is we show we assume that there exists a second one. So we assume that there exists a z prime such that it's equal to z plus mk1. So we want the z prime to be congruent to a congruent to z mod n, and z prime is congruent to b congruent to z mod n as well. So that tells us that z prime is equal to both of these guys, which then tells us that these two are equivalent. So therefore, mk1 is equal to nk2. Therefore, m divides nk2, right? But the GCD of m and n is equal to 1. Therefore, m divides k2. So, i.e., k2 is equal to m times k3, which tells us that this is actually going to be greater, which gives us our contradiction, because this tells us that z prime is equal to z plus n times mk3. This guy right here is greater than 1. This guy right here is nm. So that tells us that up to mn, i.e. mod nm, z is unique. Therefore, we have uniqueness. So you can go through and do the Euclidean algorithm to actually find this. I'm going to attach some videos of people actually going through and doing that that I think will be good for you to watch. There's also a geometric way to think about this, and you can just keep track of how many times you turn this wheel, and that will give you the answer of what is the number mod, or the number that we'll first have. So this is dealing with mod 8 and mod 7. how often do I have to turn them for the numbers to agree. So if I add, say, 3 mod 8 and 4 mod 7, how many times would I have to turn these? And each time I turn, it's like gears, they each go out by 1 before I would actually get them to agree, and that would tell me what my z is in this situation. And that's a geometric strategy for doing it, but it kind of gets out of hand. So